Pluto is relatively far away and dim, a small astronomical object that was once considered part of our solar system. However, recent and surprising announcements from well-known space experts Myoku and Neil deGrasse Tyson have brought Pluto back to prominence. They suggested that the distant dwarf planet could potentially be on a likely crash course with Neptune. They are not just hypothesizing, they're issuing a warning. This miniature world may be heading straight for a catastrophic encounter with Neptune, but how could such a thing be possible? And what kind of aftermath would there be if an enormous impact like this actually occurred? Are we observing a strange cosmic illusion, or is something far more tangible and far more alarming speeding toward us? Pluto's path comes dangerously close to Neptune's. Tyson, Neil deGrasse, and Myoku are raising the alarm. If there's even a slight adjustment, we could be facing a devastating planetary accident. Could Earth also be in danger? More crucially, how could such a cosmic occurrence even come to pass? Join us as we discuss the potential outcomes of a Pluto-Neptune collision. Pluto, once officially a planet but later downgraded to a dwarf planet, remains a source of intrigue in the vast universe. As shown by the current models from leading scientists, Pluto passes dangerously close to Neptune's orbit. Renowned astronomers Neil deGrasse Tyson and Myoku are letting the world know about a potentially dangerous interaction between these two bodies, which could imply a substantial hazard for Earth. Yet, how could this situation occur? Pluto's journey around the Sun is unlike any other orbiting body in our solar system. It takes an incredible 248 Earth years to complete one revolution. Ever since its discovery in 1930, it hasn't even made one full orbit. Still, the intrigue doesn't stop there. Pluto's orbital path is highly stretched out, much more so than the generally circular paths of the principal planets. Even more fascinating is its orbital inclination of 17 degrees compared to the Sun's plane. This trajectory is significantly more erratic than those of other planets, adding layers of complication to Pluto's movement. Arguably, one of the most fascinating aspects of Pluto's route is that it intersects Neptune's orbit. For about 20 years in each orbital cycle, Pluto is actually closer to the Sun than Neptune, defying what we'd expect based on their standard positions. This raises the typical inquiry: why haven't they collided? The answer lies in the gravitational effects of nearby celestial giants. Studies into Pluto's path began soon after it was found. Early astronomers made an effort to make sense of its peculiar orbit. While most planets move in loops that are in line with the Sun's plane, Pluto's trajectory is slanted and uneven. The puzzle grew deeper when scientists realized Pluto's orbit crosses that of Neptune. The stability of Pluto's motion, despite these strange features, proves the subtle intricacies of space mechanics. The three-body problem, recognizing how three celestial objects like Pluto, Neptune, and the Sun influence one another through gravity, is central here. It's like predicting future positions based on their initial placements and mutual pulls of gravitation. In Pluto's case, this complexity demonstrates how the Sun's movement, Neptune's orbit, and pull all work in an interlinked system. Terms like asynchronous oscillation, VZK wobble, and orbital drift are key to decoding this riddle, as highlighted by experts in astrophysics. What helps maintain celestial bodies on their stable routes is asynchronous oscillation. In Pluto and Neptune's case, this means that when Pluto moves, it is positioned along Neptune's path in a safe location, at least 90 degrees from Neptune, an angular buffer that prevents a crash. Orbital drift, on the other hand, involves the vertical displacement of a body as it moves around. Pluto experiences this, which suggests that when it draws near Neptune or another large planet, it is far above their orbital paths, adding another safeguard against potential impacts. The VZK wobble, named after Zeldovich and Kaku, who studied the gravitational interactions of space objects, is another important aspect. It describes how three massive entities, like the Sun, Pluto, and Neptune, exert forces on one another, influencing their movements. In Pluto's situation, the VZK wobble offers insight into why its orbit near the Sun appears erratic. Even though its path may seem unstable, this wobble helps keep it smoothly orbiting over very long periods. The VZK wobble shows that while space may seem chaotic and unpredictable, underlying principles still maintain a degree of stability. These forces support Pluto's consistent motion, preventing a Neptune collision or wild deviation. This three-body dynamic is vital to understanding how orbits shift due to gravitational interference. When we study it, we learn more clarity about Pluto, our planetary group, and even galaxies far away. Computational models from the 1980s indicated that, while Pluto's orbit is supported by a few features, it exhibits unpredictability. Minor changes in starting conditions can cause major deviations over centuries. Still, Pluto's orbit has remained steady over remarkably long durations. Modern automated data has allowed us to better observe how the massive planets Neptune, Jupiter, and Saturn influence Pluto's journey around the Sun. Pluto and Neptune share a special orbital rhythm. For every collapse Pluto makes, Neptune completes 3. This synchronicity helps preserve Pluto's route. But Neptune is just one of many players. Jupiter's powerful gravity plays a major role in keeping Pluto's path stable. Saturn also contributes. Studies show that Jupiter's mass is sufficient to help maintain Pluto's trajectory for possibly billions of years. It appears that Neptune, Jupiter, and Saturn are collectively working to guarantee Pluto travels safely through space, staying out of danger. These unusual but vital systems are crucial to stabilizing our solar system. Without them, space would be far more chaotic. Objects like Pluto might crash into other planets or be kicked out of the system, creating chain reactions across the cosmos. Particularly in Pluto's case, and with concerns about future encounters with Neptune, understanding its movement is essential. This improves our understanding of the dynamic and ever-changing nature of our planetary family. Pluto's case shows how even seemingly unstable orbits can achieve harmony through complex gravitational and kinetic balances. It also emphasizes the necessity of observation and analysis of these anomalies to better understand our place in the universe. Exploring the outer realms of space often brings us face to face with the strange nature of celestial phenomena. Pluto's orbit is a perfect representation of such irregularity. The concept of orbital chaos, which refers to how orbits are highly sensitive to their starting conditions, is clearly at play here. For Pluto, this means that even tiny changes in its speed or position can dramatically alter its long-term path. Using computer simulations has greatly helped researchers examine Pluto's behavior. These tools use complex formulas to replicate how Pluto and planets like Neptune interact through gravity. By tweaking initial variables, researchers can observe how even minor adjustments may completely change Pluto's destination. In the year 1980, digital models unveiled a startling feature of Pluto's orbit. Despite built-in stabilizing factors like orbital and asynchronous oscillations drift, Pluto's journey can still act unpredictably. A slight difference in its starting location or velocity could result in dramatically different outcomes in just a few years. Nevertheless, Pluto's path has held steady over billions of years. This indicates that, underneath its erratic appearance, is a secret consistency. Predicting the motion of celestial objects, especially those with erratic orbits like Pluto's, remains an enormous challenge. The fundamental instability of such systems makes long-term predictions full of uncertainty. While mathematical models are excellent tools for understanding and predicting space dynamics, they also show our limitations. These calculations rely heavily on accurate starting values, and even a minor oversight can result in drastically different results, making precision very difficult. Beyond the unpredictable nature of orbital paths, Pluto also represents the continual movement and transformation within the cosmos. Despite humanity's considerable achievements in astronomy, Pluto's unusual behavior serves as a reminder of how much we have not yet learned. Understanding how the size of planets shapes Pluto's movement helps us understand solar system dynamics better. It shows that each planet's mass and location can have a significant impact on others. So, why were astrophysicists suddenly concerned about the possible effects of Pluto and Neptune, despite every cosmic mechanism intended to avoid it? Neil deGrasse Tyson, a renowned scientist and influential figure in public astronomy, offers a unique take on our planetary puzzles, especially Pluto's unusual story. Tyson, known for advocating Pluto's reclassification as a dwarf planet, offers insightful commentary on the manner in which our comprehension of orbits and the solar system evolves over time. He doesn't see the change in Pluto's status as disrespectful, but rather as a necessary correction based on growing scientific knowledge. Tyson believes that learning and adaptation are central to comprehending intricate orbits. He views trajectories like Pluto's as a sign of how much more can be discovered, the wonder that lies beneath such mysteries making astronomy exciting. Yet, while Tyson is generally optimistic, his view of a potential Pluto-Neptune collision is far more sobering. His concern about Pluto's fate, once an official planet, stems from his understanding of orbital instability. He acknowledges that Pluto has stayed safe so far, but even tiny changes accumulating over time could lead to disaster. Pluto's orbit, especially its overlapping section with Neptune, forms a fragile cosmic rhythm that may not last forever. Tyson argues that even minor shifts in Pluto's movement may result in significant consequences. Over thousands or millions of years, such disturbances could cause chaos or even a direct collision. Though this is not an immediate threat, it's a possibility unfolding on a time scale far beyond human civilization. Still, Tyson's cautious tone stresses the importance of continued vigilance and further study of Pluto's orbit. Tyson is not the only one. Michio Kaku, a world-renowned theoretical physicist, also sees the possible mayhem that might result from planet-to-planet interactions. Kaku, like Tyson, is amazed by the universe's vastness, but he also understands the fragile equilibrium of the planet's systems and the unpredictable outcomes that may arise. Both Kaku and Tyson emphasize the importance of relentless exploration into the invisible forces guiding orbital paths and the long-term future of our solar family. In conclusion, Pluto's circumstances reflect how our knowledge of the universe is in constant motion. Each discovery opens new questions. As astronomy advances, the little chance that Pluto and Neptune will collide serves as a humbling reminder. The universe is full of surprises, and even planetary routes that appear to be tranquil can shift drastically over time. Pluto's lessons inspire us to keep looking up and to keep wondering what secrets the stars have yet to reveal.